Hello everybody and welcome back. Now that we have taken a look at the lesson for the day, let's go ahead and take a look at some guided practice problems. There is a link on Canvas to these problems where you can open them up and follow along and just kind of type the answer in as you go. Or you can just watch this video and just kind of get an idea for how to do these problems. These problems are going to be very similar to your independent practice problems that you'll turn in for a grade today. So I highly recommend at least watching this once through before you start working on that. And the good thing about virtual learning is that you can pause the video and try to answer them before I give you the answer. And you can always go back and watch it as many times as you need. So let's go ahead and take a look at problem number 1. So the image on the screen is a energy diagram. So what we looked at in our lesson today. So here we've got a reaction taking place. On our x-axis we have the time. So this is the time elapsed for the chemical reaction. And then on the left-hand side on our y-axis we have our heat content in kilojoules. So kJ, so that's the heat content or the energy of the reaction. So remember we learned that the different points on this graph indicate different things in our problem. So right here down on the bottom on our left-hand side, we have our reactants, right? On the right-hand side, we have our products. So anytime we have a chemical reaction, our reactants go in on the left and our products come out on the right. And then at the top here where this peaks is our activated complex. And remember, that's just that kind of medium in between where the reactants are, how much energy it takes to get the reaction started, and then eventually that push to the products. So we're going to just take a look at this and how to identify the energy of our reactants, our activated complex, our products, and then how to tell whether or not these are endothermic or exothermic reactions. So number 1 is asking us for the heat content of the reactants of the forward reaction. So that just means we're going from our reactants to our products. We're going to talk about reverse reactions later, so we're just keeping it simple for now. So remember, our reactants are on the left-hand side, so they're located right here, okay? And our reactants are associated, if we follow the line over, with 80 kilojoules. And that's it. That's all you have to do. You just have to find the heat associated with the line where the reactants are. As long as you know where the reactants are, you can identify the energy of the reactants, which in this case, again, this line right here is associated with 80 kilojoules. So we're moving on to problem number 2. Now it wants the heat content of the products. So our reactants were here on the left on this straight line. Our products are here, okay? So if our products are here, on our right-hand side, we're going to follow this line over, and those are at 160 kilojoules, okay? And it's as easy as that. You're just identifying the heat of the products on the chart, and because that line is associated, it lines up with that 160 value. The answer is 160 kilojoules, okay? Once you have practiced knowing where everything is located on these energy diagrams, these become pretty easy. Now it wants to know the heat content of the activated complex. So remember, our activated complex is right here at this peak on this chart. So, and here's a little orange line to help you visualize it. So right at the top here is where we're going to find our activated complex, and that's going to be associated with 240 kilojoules. So again, as long as you know your reactants are here, your products are here, and then your activated complex is at the peak right here, you can pretty much identify what the heat content is. So moving on to question number 4, this one's a little bit different. You're gonna have to do a calculation, and we all know we love math, right? So the activation energy of the forward reaction. Now remember, the activation energy is the energy required to actually get the reaction started. In terms of chemistry, we define it as the difference between the energy of the reactants and the energy it takes to form the activated complex. So we're going to take the difference between the energy of the activated complex and the energy of the reactants. Now, when I say the difference, that means we're going to subtract. So we're going to start with 240 because that's the energy of the activated complex, and we are going to subtract the energy of the reactants, which is 80. So we're going to do 240 minus 80, and that's going to give us 160 kilojoules. So the activation energy, the amount of energy it takes to get this reaction started, to get the products formed, is 160 kilojoules. Now it's asking for the delta H. Remember, your delta H is your change in heat from the reactants to the products, okay? So here, when we're calculating our delta H, we're going to take the energy of the products of what we end with, and we're going to subtract what we started with, okay? So our end energy in our products was 160, and then the energy that we started with in our reactants was 80. Okay, so remember that the delta H, the entropy, is just the loss of heat or the gaining of heat in the system, depending on if you're talking about exo versus endothermic reactions. But in this case, this delta H is going to be 160, again, the value of the products, minus 80, which is the value of the reactants. And so we've got 160 minus 80 to give us a positive 80. So it's important to understand that your delta H, if you remember from the lesson you just watched, can be positive or negative, and that's going to tell you whether or not it's an endo or an exothermic reaction. So now that we know that our delta H is positive, let's go ahead and answer this question. Is this an endothermic or an exothermic reaction? So remember, there's two ways to tell. Number one, is your delta H positive or negative? And number two, what about the energy of your products versus your reactants? In this diagram, we can see that the energy of our products is higher than the energy of our reactants. When that happens, so when you've got a higher energy in your products and you've got a positive delta H, that's going to be an indication that you're working with an endothermic, or you have an endothermic reaction taking place. Again, that means the system is taking heat in. Okay, so it's pretty easy. So you can do this either just by looking at the graph and seeing whether the reactants or the products are higher, or you can just do it by calculating your delta H. The delta H is positive, it's endothermic. All right, so let's look at another one really quick, and we're going to go through these pretty quickly since we already did a set just like it. So 7 is asking for the heat content of the reactants. So again, here are our reactants. We've got 2 going into this particular problem. So our reactant energy is right here on this line, and that's going to be associated with 40 kilojoules. Again, simple as just identifying it on the graph and then finding the value on your y-axis. Just like before, it's asking us for the heat content of the products. So again, reactants on the left, products on the right. Here we have C and D are our products on this line, and if we follow that over, we are at 20 kilojoules. Okay. Now we're asking for the heat of the activated complex, or the energy of the activated complex. Remember, that's at the peak, and this peak, if we follow it over, is right around 100 kilojoules. Okay. Now it's asking for the activation energy for this particular example. Remember, our activation energy is the difference in the energy of our reactants and our activated complex. So if we remember, our activated complex energy was 100 kilojoules and our reactants was 40. So we're going to do 100 minus 40, which is going to give us 60 kilojoules, meaning it'll take 60 kilojoules of energy to get this reaction going. The enthalpy change, so your delta H of the forward reaction, we are still going to do the energy of the products minus the energy of the reactants, okay? You always want to subtract the reactants from the products, okay? Because remember, it's okay to get a negative number. So you always want to make sure you're subtracting your reactants from your products. So if we start with our product energy, we got 20 kilojoules right here. And we're going to subtract the 40 kilojoules from the reactants. So if we have 20 kilojoules minus 40 kilojoules, that we're going to wind up with a negative delta H this time. So our delta H is negative 20 kilojoules. So last thing we need to do is identify whether or not the forward reaction is endothermic or exothermic. So 2 ways to do this. Number 1, by looking at the delta H, which we know is negative. And number 2, looking at the energy of the products versus the reactants. So here our reactant energy is higher than our product energy. And when that happens and we have a negative delta H, that's an exothermic reaction indicating that your system is losing heat. So heat is being released. All right, so that is it for your guided practice problems. I hope this helps. Your independent practice problems are very similar. So if you find yourself struggling, you can always refer back to this video, or you could always reach out and schedule a tutoring session, or just send a quick email or remind, and it might be something that we can clear up pretty quickly. So I hope you guys have a good day, and I hope you have an easy time with your independent practice today. Again, thank you guys for sticking with it and continuing your learning during this time. I know it's pretty stressful for you guys, and it's stressful for your teachers as well. But again, we are all in this together, and we are making the best of it. So if you guys need me, let me know, and I hope you all have a wonderful day.